climate projections webinar series. Very much appreciated, and I hope this is a useful, a constructive use of your time. So I'll be giving the first presentation today, and I'll be followed by Dave Sexton. I'd just like to hand over to Sitlali now, go through some of the housekeeping.
Hello, everyone. Thank you for joining. We ask you to please write every questions that you have for the presenters in the Q&A box, and not vote the questions, so that the chair can choose the questions that you want to mostly be answered. Please use the chat only for technical issues. There will be a short survey feedback in between speakers. That shouldn't take much time. You will be muted and off camera unless we enable you to speak and you ask to do so. The webinar is being recorded. It will be afterwards be put on the Met Office Science and Services YouTube channel, so you can catch up on it afterwards if you want. If you have technical difficulties and cannot use the chat, please contact ukcp.usernetwork@metoffice.gov.uk or use the chat function again. And please, if you have UKCP usage that you would like to present or you would like to share with us, please let us know at ukcp.usernetwork@metoffice.gov.uk. Any usage is very welcome. Thank you very much, and I'll give space to David Viner. Thanks.
Is this working out? Here we go. Yeah, just echoing Sitlali's points there. This is your community. Please do feel free to really put out your suggestions. The survey is very important, and also, we want to hear back from a wide as possible cross section of users of the UKCP data about what they're up to with the data, any issues about the use of the data, what they'd like to see for the future. So this is a two-way conversation, and it's important that we get your feedback and we get your responses about how we can take things forward as well, because we want to really share the experience across this wide and diverse community of end users who are using the data. So I've unfortunately missed a couple of the last webinars just due to other commitments and something else called the summer. But I was just reflecting on where we are with climate risk, and I was just really exploring some of the things that have happened in the past, and I was going through some presentations of mine from the past, some very old presentations, and I've got a couple of slides from those. I hope you provide some context to where we are. So, in terms of the starting point, I've got a quick question for you all here. It's coming up to the Christmas period, the seasonal holidays we're having. You'll all be doing your office parties, office quizzes, family quizzes, and I hope everyone who sits around the table on 25th of December on Christmas Day, does construct a quiz about climate and the weather, because it's fascinating, and I try and do that every year for my family. They seem to vacate the room though. So here you go, quick question. What has to be lower than minus 34.39 Celsius for the remainder of this year to beat what record? And if you've got any answers to that, please leave it till the end of Dave Sexton's presentation, and we'll just have a quick review on that. It's an area of mine I always find fascinating, and I've got a nice seasonal picture here of England, at least, not covered in snow and people sledging, just damp, soggy fields that we see right across the countryside. Just again, where are we? What's happened? These are the significant climate anomalies as recorded by NOAA, and let's hope next year they can continue to do this. And we can see, as every month shows, a whole range of extreme events that have been occurring around the world, some of them devastating. And I won't dwell on some of the more recent ones, which have caused a great deal of profound devastation and loss of life, some nearer to home than others. But again, right across the world, we're seeing a whole catalogue of extreme events. You can look at those in Malaysia. 3 super typhoons hit hit the Philippines. We've had records broken. The global sea ice extent for October was ranked the lowest on record. So we're seeing these profound indicators of change happening, being reinforced every year, and that coincides with the global temperature. And one that stuck in my mind, it's not necessarily from this year, but it didn't really get that much coverage, was a seismic signal was detected across the world for 9 days. Every 90 seconds, there was a vibration that was detected in numerous seismic sensors around the world. And eventually they worked out that on the 16th of September last year, there was a huge rock and ice avalanche in Greenland. And this was put down to climate change. This is the melting of the glaciers. And this event, dished out 33 million cubic meters of rock and ice. It caused a tsunami in extent of about 600 foot. And because of the enclosed nature of the valley, it just resonated backwards and forwards for about 9 days. And this is becoming more and more frequent. Some are witnessed, others like this one went unnoticed until they actually provide a location. But it's just another indicator of what's happening and the rapidity of what's happening as well. I was looking at the historical context of where we are and how things have changed over time as well. And again, this is the CO2 concentration. First of all, we have John Tyndall, who the Tyndall Centre was named after, undertook the experiments to demonstrate clearly, and these have been repeated, that carbon dioxide, methane, and other gases had a radiative property, i.e. they trapped heat into the atmosphere. And that was really the first piece of the jigsaw around where we are with human-induced climate change. In the early 1900s, Svante Arrhenius postulated what would happen if CO2 doubled in the atmosphere. He couldn't measure it, but he postulated what would happen. He indicated that if CO2 would double, it would warm the planet by about 4 to 5 Celsius. Not too bad. And he should have been given the Nobel Prize. And a piece of trivia I was passed on by one of the other people on this slide was that he would have been given the Nobel Prize if he hadn't been having an affair with Nobel's wife. So there's one for the trivia books there. The third piece of the jigsaw was really Keeling. David Keeling put together and constructed and started the Mauna Loa Observatory looking at CO2 concentration. And there we have the Keeling curve, which shows the seasonal variation in CO2 increasing over time. And in the mid-80s, the Climatic Research Unit, so we've got Phil Jones at the top there and his colleagues at the Climatic Research Unit, put together the global temperature curve for the first time, showing the world warming. James Hansen followed that up in Congress, stating that climate change was being caused by human activity and it would only get worse. And then we see the whole thing telescope. And an interesting perspective on this comes from, I got this from reading a book by Nobel Yuval Harari, I hope I got his name right, Sapiens, and it showed how things concatenate over time. And I couldn't squeeze everything on, but these two figures here just show the scientific climate change publications per day. On the left, we have those I just mentioned, climate change. We have those on the right that mention extreme rainfall, and this exponential increase in the literature. The studies, the wealth of studies that have gone on around the world. And this ties in with the IPCC assessment report cycle. So you're looking at tens of thousands of papers that have to be reviewed within each assessment cycle. I was part of the 6th assessment cycle. I think Working Group 2 did about 40,000 papers were covered in the review. That's only going to increase for the 7th assessment cycle. And the wealth of literature that is underpinning what we know, and all the governments agree to what's happening. They might have different views on how to deal with it or not deal with it, but we know the evidence there is increasing, and it's increasing on a daily basis. If we look at that in the context of time, and this is where it really came from, the Sapiens book. 100,000 years ago, Homo sapiens shared the planet with at least six other human species. We don't anymore. Some of those species have been assimilated into our DNA. We know that through DNA analysis. But during the depths of the Ice Age, about 70,000 years ago, we had the cognitive revolution. And as we came out of the Ice Age, the agricultural revolution 12,000 years ago. And for some, that was the start of the beginning. For others, that was the beginning of the end for human civilization. Depends on your perspective on life. And then things potted along, didn't really change much. And in Sapiens, it points out that if you look at moving someone from the 5th century AD to the 15th century AD, not much had changed. human society had changed, the political structure may have changed, but technology hasn't changed much. And then we had the Age of Enlightenment. The scientific revolution began. Our understanding of the planet increased a great deal. We knew what was going on. The scientists were putting our perspective of Earth in the greater context of the solar system and the galaxy and the universe. And then 250 years ago, we had the start of the Industrial Revolution, mainly generated from the United Kingdom. And this is where I've been spending my career correcting it in my wife's side of the family. One of her relatives was George Stephenson, who invented the rocket and helped perpetuate the age of coal and the age of the industrialization, not just the UK, but wider afield as well. And then the industrialized world kicked on rapidly. And then 15 years ago, probably what was the next big transformation, the smartphone age, and how that has concatenated time, concatenated space, concatenated how we deal and talk to one another. The SSPs, the shared socio-economic pathways, give us an indicator of what may happen to the world. This is based a lot upon the SRES report, and I used to use the SRES storylines a lot for, setting in context about where we're going and giving people that end users, stakeholders, that wider picture of the direction of society. We couldn't judge it entirely, but if you look back to, 20 years ago from the SRES, where we've changed. We were at one stage looking that we might be heading down this SSP4, SSP1 type pathway. But unfortunately now, if you look at where we are here, we're probably along the lines of the SSP3 pathway, the increased focus on security, barriers to international trade, higher inequality, low population growth in rich countries, higher in other countries. And this looks like where we're heading. Things can change very quickly, of course. And we know what that means within the global context of climate change and the temperature. I'm one of life's optimists. Every year, at the start of the football season, I sit there and think, right, Liverpool are going to win another major trophy. Okay, and to be fair, that's been proved right. And that probably underlines where I'm on my optimism. But with climate change, I'm increasingly becoming more pessimistic. And I don't want to sound gloomy at this time of year, but this is, I think, the scientific reality. So a question back is, are we actually planning for the right future? Are we really looking at trying to think that we're going to hit the 1.5 degree world, the 2 degree world, or are we really going somewhere far different, somewhere where we're not going to be comfortable with? And are we trying to be reluctantly avoiding that future because it is quite unpalatable? And as a result, are we building in the right levels of resilience and adaptation to what we're doing? So there are a whole range of complex barriers to solutions. This is work I undertook a while back. It's still the same. We have cognitive, normative, political and economic barriers. I'm not sure this animation is going to work. Yeah. So lack of understanding of the science, still relevant now as it was 20 years ago. There's denial about what's going on. We have a north-south divide in the globe. It's always perceived as a problem for the next generation. Even when I started this 30 years ago, it's in the future. People still think it's in the future. We know now, 30 years later, it's happening now, but people still are trying to bat it down the road, kick the can down the road. And then we have the economic system is organised around fossil fuel production, still the case. We're still fixed on that. The reverse of that, go forward, is what makes something resilient. So if you take those barriers, reverse them, how can you build a resilient, aware organisation? It's making sure that any organisation is aware, it's diverse, it's flexible, it's objective, and you integrate those. In some essence, this is what some people might call woke. It's an aware system. It's something that knows where it is, its place in society, its place in the world, and it's addressing those issues to make sure it can stay resilient. Hopefully these slides will be shared so the detail on this can be picked up. There's a shed load of work being done now on the resilience dividend, and this is work I did when I was at Mott MacDonald. Fortunately, this is an animated. Know that a resilient organisation, a resilient system, can survive the shock and can bounce back better. Those that aren't resilient won't survive the shock. They may be able to retrofit, they may be able to, repair, replace, but they may never get back to where they started from. So this hysteresis is important in the business context and a business operations sense. It's important that this is reflected in planning and decision-making requirements. So we know from the work that if you plan for it, spend a dollar or a pound or a euro on resilience, it should give $5 to $12 or more benefit in the future. Now, that's always difficult to explain in a financial sense, especially when you start looking at financial planning, comparing what's the OPEX expenditure against CAPEX, and how you work that and you factor that into the future. And there's evidence around that from some of the financial initiatives that are going on. But this resilience dividends is an important context to put forward when you're demonstrating why we need to adapt and build resilience to climate impacts. Working Group 2 looked at adaptation. This is a figure from chapter 17 of the Working Group 2 report, looking at adaptation typologies and where we are. And this is a collection of all the literature, the thousands of papers that were reviewed in chapter 17. And I'll admit I was an author on chapter 17, so this is important work. There's extensive protection, moderate investment focused on adaptive capacity, and little adaptation investment. And we know that if you put in extensive protection, you reduce your exposure, you reduce your vulnerability, and you might need more money to spend to do that way, but your residual risk is reduced. The opposite of that, of course, is little adaptation investment. Got large residual risk. You haven't really affected exposure. You haven't really affected vulnerability. And at the moment, most of the adaptation and resilience responses are around the middle curve, where we're seeing just enough at times, in most cases not enough, and we're still underspent globally and systematically on adaptation and resilience. Oh, so I lost some of this. This is the IPCC diagrams at risk. Risk is a function of exposure, vulnerability, and hazard. Over time, it's dynamic. You can't look at risk in a static context. You've got to look at how the hazard will change. In a climate context, very few hazards are going to decrease. Most will increase. The only hazards that will likely decrease are the ones related around cold. Exposure can decrease if you're spending a lot of money. Vulnerability can decrease if you spend a lot of money on reducing vulnerability in education, awareness, and early warning system. In my view, and it's quite physical climate risk is not an ESG issue. Physical climate risk, in a practitioner sense, is an operational issue and a business continuity and business survival issue. If you look at this from an ESG perspective, you're going to undercook it. So it's important that organisations see where physical risk is, the actual effect it's going to have on operations, effect it's going to have on livelihoods, etc., all the way down the line, however you categorise that. And then assessing physical climate risk, looking at where the hazard comes from. Of course, that's the UKCP data in the context of the UK, but the climate change risk assessment is one part of iterative climate change risk management. And this is again from chapter 17. It's a small piece at times of the decision making. So we can sometimes over-focus on the climate risk side. We can sometimes over-focus on the hazard because it is part of this larger picture. Other factors come into play. The decision making has to be understood. It's a very complex area, or at least I found it very complex when I delved into this, about how decision makers come to their conclusions and come to their analysis and how then they react and put that into operations. But we've seen climate change risk failure. These are two that rattled me a bit. The one on the left is the A421 through Bedford. This is just a failure of adaptation, resilience, or whatever you want to call this. However you look at this, this is a failure. It rained a lot, to be fair. This was an underpass that was designed to be drained only by a pump or a couple of pumps. Basically, a couple of buckets would have been better. It failed, flooded, 2-3 weeks out before they could get this back operation again. Tens of millions, hundreds of millions of pounds spent on this road, and yet they didn't account for climate impacts properly. And then Thames Water, I won't pick on Thames Water because all the water companies, I'm not just picking on Thames Water because all the water companies are culpable for this. Sewage going into the rivers. A spokesperson said it was unacceptable, but it was due to excessively heavy rain causing high groundwater in river levels. That was their excuse. They blamed it on something that we've known about for decades. We know rainfall intensity is increasing, and we know roughly what the order of magnitude and the scale of that is. Ignorance is not an excuse here. No public body, roads, no public infrastructure body should be using, oh, it was too hot, too windy, too wet as an excuse. With the climate science community, I've been telling them this for a long time. This is a copy of a slide, a screenshot of a slide I was using in the late 1990s, looking at, and this work that was based from by Tim Osborne at the Climatic Research Unit, looking at what would happen to mean and extreme rainfall events in southern England. We know that going to be big changes, and we can see those happening. The photograph is something I took nearby where I used to live in North Norfolk. We think this was 80 millimetres of rain in less than an hour. And so these events were happening. So to use, oh, it was raining too much as an excuse is one that shouldn't really cut. So it's important to say that we need to factor in the right levels of the hazard, the change in the hazard, as soon as possible into all current and future design. And it's still, the question is it being done properly? So this is something I found from, I don't want to name and shame, but anyway, you can work it out by cutting and pasting. This is guidance for climate change risk. And I've seen this from the end of someone who was having to analyse the climate change risk assessment using this type of guidance. So I was looking at I've been asked to look at climate change risk assessment for investment on a solar farm, and let's just say it was in a hot country, not in the UK, but somewhere else. The technical advisors have come back saying, right, solar panels have got an operational temperature up to 45. We've done our analysis. The average mean summer temperature for this region they were looking at was about 28 Celsius. I found within minutes that the record temperature for where the solar farm was going to be planted was over 46 Celsius, higher than the operating conditions. But they said, no, we're following guidance. That if the mean summer temperature should be used, or the mean maximum summer temperature. So this is recent guidance. It may have been updated. I'm happy to be corrected. But again, this is for Stansted Airport climate expansion, where they didn't look at the absolute maximum temperature that could occur. And we know already, we can look at this somewhere. We know Stansted has experienced in the last 3 or 4 years temperatures in excess of 40 Celsius at least twice. So is this fit for purpose? Is this guidance fit for purpose? Are other guidance documents fit for purpose? Are the data being used correctly? And I'd just like to finish with just a couple of slides, just a few questions. On the right, we have sort of cascading, compounding, transboundary hazards and impacts based upon the IPCC Work Group 2 technical summary, looking at complex risk. And it is. But the questions I want to pose, and this is not just for now, but for future, about how we do climate change risk assessments. Do we have the data to undertake a very robust assessment of the 3 components of climate risk? Is the analytical capability in place to look beyond single asset, single temporal and single spatial domains? Because no asset exists in isolation. They're connected. Most climate change risk assessments look at a single asset within a fixed boundary. That is not the reality. Can we address compound, cascading and multi-spatial risk in climate change risk assessments for practitioner applications? And the reason I ask that is because to do that is quite a sophisticated, complex process. Most budgets for climate change risk assessments are in the tens of thousands of pounds. And is current climate change risk assessment practitioner guidance good enough? Is it too convoluted? And is it consistent across sectors? So I've seen a plethora now, explosion of different climate change risk guidance documentation, some of it conflicting at times. So if we're going to do this properly, do we have to answer these questions in a positive way? Or do we just look at our single focus, our single sector, single asset approach to what we're undertaking now? Okay, thank you very much. Do I stop sharing now? No, I don't. You have to take control, Sitlali.
Thank you very much for that. I think that was a very illustrious chat about, and a little bit boring. Please remember to put your questions in Q&A if you have any questions you would like to make to David Weiner. Whilst I have a chance, I would like to ask, do you think the extreme events that we're having now will be good enough to convince the organizations that need to be convinced to take action?
It's only often the case where we have reactive and retrospective awareness. Once organisations take note when they get hit. But what I was pointing out in those slides about the road and the water and that, and there's just two examples that when I listen to them read about them, sort of, they shouldn't have an excuse. The scientific community know what's coming by and large. We might be underestimating some of the rate of change and the magnitude of some of the extreme events, and the events in Spain were shocking, but they were off the scale. So were the floods in Germany a couple of years back, off the scale in terms of temperature recorded and experienced. But we shouldn't be in a position of saying we didn't know, because the work of the Met Office and other Met Service and the scientific community has demonstrated that we're going way beyond where we're used to be, and we have to look more actively at what the worst case scenario is. And I think that comes back to where we're sometimes constrained by organisations saying, well, can we just stick to a 2-degree world or a 3-degree world? We don't really want to think about something that may be a bit more unpalatable. But it's not the actual endpoint that's the issue, it's the rate of change that is going to be the issue in the near to mid-term. Okay, right, there's no questions yet. I presume everyone's running around looking for the answer to my question at the start of my presentation. So Dave, while waiting for questions, I'll hopefully I'll hand over to you, and hopefully all that works. So thanks. So I'd like to just introduce Dave Sexton. I mustn't forget that. David joined the Met Office Hadley Centre in 1993, so quite a youngster in this context. And he looked at attribution and detection work. And then since, almost for a long time now, David's been working to look at addressing inherent uncertainty in the climate system. And I mustn't forget it, must have missed this one out. In 2008, he won the L.G. Groves Award for Meteorology for looking at pioneering work on probabilistic climate projections. And he's now a science fellow at the Met Office, with the aim to look at how to make data more usable, easier to use, and safer to use, which is a good perspective on this as well. So Dave, over to you.
Thank you. Sid Ali, is it okay if I share my slides, because they didn't work quite well, did they?
Yeah, please go ahead.
Okay. Oh, what's it gone there? Okay. We're good. Okay, the Teams is doing an interesting thing again. It's trying to hover over what I'm trying to say. So if it gets in the way, that's a problem. Anyway, thank you very much. It's great to talk to you. Very much in the Met Office is always trying to kind of improve the information we deliver on climate projections. We can either do that by giving you more data and delivering more, but one of the other ways of doing it, which you might not see other than outside UKCP 9, UKCP 18, is that we're always trying to pull through that understanding of the climate, trying to bring in that improved understanding to improve our way that we communicate climate change and provide guidance, which is a really important aspect and kind of touches on what David said about like safe to use. So very much in that vein, today I'm going to be talking about describing future UK winter precipitation in the terms of changes in local circulation patterns. We also like to listen to other scientists and find out how to do things better. So one of the really important things is listen to the social scientists who have argued that good communication around risks in climate hazards requires a couple of things, essentially. One is to explain the information in a user-relevant way, and the other one is to help people better understand the factors that control the risks, because if they can understand that, then they're going to use the data in a better way, and they will also build their confidence in the data. And so ever since I was heavily involved in making the probabilistic projections in UKCP 9, I've really looked for clearer ways to move beyond those kind of long-term averages we did then and talk much more in terms of variability and extremes. really moving towards talking about the weather in the future climate. So in UKCP 18, in that vein, we added 2 products, which were plausible realizations from climate simulations at the global scale, but also at regional scale, so the 12-kilometre and the 2.2-kilometre runs, the latter being incredibly popular. And these products are essentially aimed at providing information on variability and extremes. So we have, I'm going to be talking about different climate simulations in this talk. So just to recap on UKCP Global, they were basically a collection of 2 ensembles. One was from the CMIP 5 set of international climate model simulations, and we used 13 quality control runs there. And then it was 15 plausible members that we made from a set of simulations that my team made in UKCP 18. I'm not going to go into what a perturbed parameter ensemble is, but basically it's trying to use one modelling framework to generate a range of projections in a kind of sensible, plausible way. And then from those 15 runs, we actually took 12 of those runs and then used those to downscale the information at the 12-kilometre and the 2.2-kilometre situation. So at the very regional scale, we're only sampling Met Office models, and that's going to be important later on. So essentially my talk's in 2 parts. The first is to touch on that first social scientist angle, which was to try to explain the range of projections in a way that people can relate to. And so what I'm going to try and do is describe the weather, certainly the UK winter precipitation, in terms of changes in the frequency of weather patterns, so the kind of pressure patterns that you might see on television forecasts, and also the amount of associated rainfall with those pressure patterns. And then the second part will be how representative are that small set of realizations in UKCP regional and local. And my aim here is to help you and me understand the robustness of that information in terms of the context of the full range of projections. And I'm going to use the very large scale atmospheric dynamics to help explain that angle. And basically, essentially, come on to when and why we might want to be careful about when we just use UKCP regional or local. So going back to the climate simulations again, for the first part of the talk, I'm just going to be focusing on the 15 global model runs that we did for UKCP Global. I'm not using the 13 CMIP 5 simulations. For the second part of the talk, I'm going to be concentrating, I will bring in information from the more later CMIP 6 set of international climate model runs used for the most recent IPCC. So, right, part 1. So I'm going to talk about UK winter precipitation. So this slide just shows you the average across the different countries of the United Kingdom. So we've got the UK in black, but also Scotland, Wales, Northern Ireland and England. You can see actually Scotland is on average, and climatologically it's the wettest of the countries, and actually that also has the biggest trend. But Wales also will get significantly wetter as well. But generally all the countries have a trend in their winter precipitation. If you then look at the year-to-year variability, and I've done this by, again, looking at the 15 individual runs, then I've looked at the amount of variability in kind of shifting 30-year windows and then averaging it across the 15 runs. You can see that actually generally there's a small change in year-to-year variability for all the countries, except for Wales, which actually has a bigger increase from about 2025. And variability, changing the amount of rainfall you're going to get from year to year, really presents an adaptation challenge. So my purpose here is going to be, I want to talk about, break this down a little bit, and I want to talk about it in terms of the daily pressure patterns that we see in the runs, how the frequency of those pressure patterns change, and how the associated rainfall changes with those. So I'm going to use a tool called weather types. Now the forecasters at the Met Office who work on the weather forecast, they have 30 weather types. So they've classified the daily weather pressure patterns into 30 types. But for climate work, that's quite complicated to use all 30. So we actually have a set of 8 where we've kind of classified them more broadly. And so the 8 types look like this. So there's a very kind of flabby, kind of northerly pressure pattern, which is hard to define really, but it kind of gives you the northerly and northeasterly weather, which in winter can be cold and crisp or snowy. It's not the only weather that can produce snow, as well, I've found out today outside, because it's snowing in Devon. But But also there's the westerly, which brings you the mild, wet winter days. The southwesterlies, which bring you the storms. And then there are other kind of various pressure patterns with different positions of the high pressure pattern. This one will create nice clear days probably. And then if you look in the actual simulations, you can see that if I plot the frequency and the number of days per winter that these different weather types happen, then you can see that weather type 2, so the westerly pattern, becomes more frequent. It's projected to become more frequent in our Met Office runs at the expense basically of this more northerly easterly pattern. So we're expecting now milder, wetter winters for that reason. It's difficult to see what goes on with the other weather types, but what I've done here is shown the percentage change in frequency for the different weather types for the last 50 years compared with the first 50 years of the 200-year runs. And you can see that generally, these three actually have increases in frequency. So the westerly, southwesterly, and the UK high, whereas these three all decrease in frequency. So then what you can do is you can also look at the amount of rainfall that's associated on the days when you have weather type 1 or weather type 2, and you can look at how that that amount of rainfall intensity associated with those daily pressure patterns on average changes in the future. So here shows you in the last 50 years of the 21st century that generally there is a greater rainfall intensity in pretty much all the weather type patterns across the 15 different projections, except for maybe weather type 1, which is a bit of a mixed signal, and the northwesterly pattern, which is showing actually a decrease in rainfall intensity, which I don't understand at the moment. But generally you see an increase, and there's lots of reasons why rainfall intensity can increase. It could be like the storm moving more slowly, but the most general first order effect is the fact that the warmer atmosphere can hold more moisture, and therefore there's more to rain out. So now what I'm going to do is I'm going to decompose. I'm going to look at the precipitation changes projected across the different members, and I'm going to decompose them into contributions that I see on different days with the weather type 1, weather type 2. So I'll show you this plot, which has got the 15 members across the bottom. They've got funny little numerical IDs. Don't worry about that. But I've ranked them from left to right, so that the blue column, which is the projected change in precipitation change in winter from the last 50 years compared with the first 50 years of the 20th century, is ranked from the smallest changes through to the biggest changes here. And if I zoom in on the first two, so you can see it more clearly, then on this plot, what I've tried to do is I've tried to decompose it to say which weather types are contributing most to this increase. So if it's above the line, then it creates a positive contribution, and if it's below the line, it's a negative contribution. So you'll see here that generally, if you look across the ensemble members, it's basically the green and the pink. So it's those westerly patterns which are producing the big changes up here, but also you see a steady kind of contribution from more rainfall from southwesterlies by the end of the 20th century. The white pattern is the northerlies and northeasterlies, which reduces in frequency and gives you less rainfall from that. Again, focusing on the UK, but now there's a different way to decompose it. What I can do is I can then also work out whether what happens to the change in rainfall if I fix the frequency of the weather types, but just allow it to see what happens if I incorporate the changes in rainfall intensity, or vice versa, fix the intensity and allow the frequencies to change. And that way I can split it into what's coming from intensity and what's coming from a change in frequency. And you can see that the ratio between the blue and the grey bars here varies across the different members, but generally towards the end is clearly the intensity that is dominating the contribution. So it's having that more moisture in the atmosphere. But there are different runs where frequency also changes. And if I go down a little bit more detail about where the change in frequency comes from, it's basically from the storms. So the storms are going to become more intense. If I want to look at the different countries, I tend to look at the 15 runs averaged together, in which case you can see that actually for UK, it's more from intensity than frequency. But for Scotland, it's a pretty even mix, actually. So it does vary from country to country. But generally, you see robustly, it's whether it's the westerlies and the southwesterlies that are contributing the most increased rainfall. So in summary for this part, the enhanced weather precipitation is largely due to an increased tendency towards westerlies and southwesterly conditions at the expense of the northerlies and easterly conditions. And it's really, there's more intensity in the rainfall, and that's most notable in the storms that come with the southwesterlies. So now I'm going to go to the second part of the talk, which is about the robustness and the representativity of those 15 or those 12 regional scale runs. And for that, I'm going to look at the large-scale atmospheric dynamics. It's very hard to say anything. It's so noisy and there's so much variability at the small scales. But really, the weather patterns, these pressure patterns, are driven by the larger atmospheric scale dynamics. So there are two main ones to look at. The first one is what I'm calling the stratospheric polar vortex. So in winter, there's up aloft above the poles, there's a rapidly kind of very cold, stable layer which spins around rapidly in a westerly direction and actually transmits that westerly flow through to the atmosphere, the troposphere where we live. And you get that sort of promotes a westerly circulation. But you've always got kind of waves, ripples that come up from the lower atmosphere, which if you get enough of them, they break like they do on a beach. Waves on a beach break. These waves can break in the upper atmosphere. And if they are large enough and there's enough of them, then they can actually disrupt this flow. And you'll see that you get all sorts of, you start getting cold air moving out further south across the North States and then across Europe and us. The positions of where the cold plunges are will change from year to year, but generally, you'll see a much more wandering kind of jet stream, a much more extreme rain weather. So this polar vortex is really important, and you can see in our runs that in the 15 members, actually a lot of them just show quite neutral conditions, but actually the 5 of them show very, very strong changes towards a more stabilizing effect, so promoting more westerly flow. So that gives you a bit of a clue where the more westerly flow comes from. And if you actually look in detail about what the strength of the polar vortex looks like in individual members, and I picked the one with the greatest change, actually the strength of the polar vortex really doesn't change that much. It gets a little bit more stable, but actually what's happening is this disruptive pattern really does become quite a rare thing by the end of the 21st century. It only happens a couple of times there. So that's what's happening. You're losing this kind of northerly and easterly flow because you're not losing these disruptions. The other one that's really important is the tropical amplification. So any change in the temperature gradient between the equator and the pole can shift the jets, and of course that controls our weather. So if you have more warming aloft in the tropics, then that tends to push the jets polewards, and you tend to increase the westerlies for that reason. So now, if we look at our 15 global model runs, the blue dots, and we look at the other models, so CMIP6, we can kind of start to understand how well our models are exploring the large scale and what that means for our local scale projections. So if you look in the first part of the first 30 years of the 21st century, you really see that the blue dots and the orange dots are kind of covering the same sort of part of this changes in the tropical amplification and changes in the polar vortex strength. So it's those two large-scale drivers. The model runs are exploring a range, and their two ensembles are showing similar things. But when you go to the end of the 21st century, you see suddenly now that the 5 or 6 runs from the Met Office model are actually promoting much stronger changes in the polar vortex strength. More so, they're also, because these runs tend to warm faster than other model runs, they tend to only explore the top half of the tropical amplification. Both these changes are pushing it to more westerlies. So that's really important. Just through the nature of the model, we're actually promoting and skewing the way we sample future climate change with more westerlies. Excuse me. So nearly finished. So the sorry, I've got another window that's popped over. So the changes in the frequency of the pressure patterns I showed you in the first half are consistent with those changes in the large-scale drivers of the winter circulation, which is great, and it really helps us have more confidence in the runs because it's doing what will happen in reality. But by understanding the large-scale drivers, we've also been able to assess the robustness of those runs. So if actually you're using the regional model runs and you're looking for things like wind speed and westerlies, you might want to look at the other CMIP6 runs, because they will have a kind of more cold, dry spells. So if wind droughts, if you like. So if you're looking at renewables, that might be one area where it's important to understand that the local models are not as representative as the whole set of international climate models. And finally, we're doing something about it. So Chris Short and his team are now driving, or have driven, UKCP Local with some of the CMIP5 members, which might do a better job in this. I haven't looked actually at that particular example. But this will improve the consistency between the full UK's global data set and the local data set. And these will be published in the near future. And there are probably people online who've got more information on that. And then finally, it's a real active area of research to look into these large-scale drivers more detailed. So that's something I'm very keen to do. Thank you.
Dave, thanks very much. We've got some questions coming through. Yeah, most of them are, relevant to both David and myself. I'd just like to just pick up on one, which that would be, will there be a UKCP Christmas quiz? So no one's yet answered my question from the start, so I just want to pick that one up again. But Dave, the use of weather types here, this is, gives me a nice warm feeling. This is something that I remember doing when I was at university, so a couple of years ago. And what we used to know at the time, Lamb weather types. So Hubert Lamb, who founded the Climatic Research Unit, made one of his names in classifying weather into weather types. And one of the first, the UK government, or what Department of Environment, back in the early 90s, funded the Climatic Research Unit to validate the Hadley Centre's climate model, and they came up with using weather types as a way of validating the models, because they had that larger scale perspective, rather than trying to look at individual groups, etc. So one of the questions on here is the UKCP weather types data available to the public? That's from Yuting Chen.
So it is. I think we did publish some information on the weather types from the 15 runs, and probably at actually the wider CMIP5 global, for UKCP global, where we could get the daily pressure patterns. So for all the 15 global Met Office runs, but some of the CMIP5 runs, we also published some diagnostics on the jets as well. So that should be available. And if you can't find it, I'm sure I can find someone who will tell you exactly where it is.
And I think also remember this, the British Geological Survey, and there are other geoscience organisations available, but the BGS did something using UKCP data on weather types to look at the stability of cuttings. But I couldn't give any more specific information on that. I think also, Dave, you'll be aware, running the code through the climate data to determine weather types is not too sophisticated, but I stand to be corrected now, because things have moved on since the 1990s when this was done by colleagues of mine. So yeah, that's a useful, I think, that's a useful resource, and one where you can use the weather types to downscale as well. But just going on to one of the other questions, Alice, by Susanna Lincoln from CFAS. Susanna, if you're in Lowestoft, a good distant way from the other side of Norfolk. Lowestoft in Suffolk, isn't it? Don't talk to one another. In your opinion, is it time to change the narrative about how we communicate the science of climate change around extreme events? In the past, perhaps we shied away from the messaging around those to avoid causing unnecessary panic. What do we think? So, you can categorise, this acute and chronic type of events. So the acute ones being the short, sharp, extreme ones. So July 19th, 2022 heat wave type event, that peaked in one day, 40 odd Celsius, very intense rainfall events, those acute events that cause a lot of problems. They're the ones that generally cause that impact and a devastating impact. But we can't shy away from those chronic changes, rising sea level as well, which will cause a different response to a storm surge. So those extreme events are the ones that cause the problems. They can't be ignored. And there's no again, with my view here, there's no real excuse for ignoring what we know about extreme events. If it's happened, so a certain rainfall event that happened, it's going to happen again, and it's likely, the extreme version will be, the next day's version will be higher. So we've got to plan for that worst case scenario, and that's my view. And just ignoring that might come down to, or not taking that into account, might just come down to an economic case around, well, it's too expensive to do that, and we'll just have to deal with it when it happens. Dave, I don't know if you've got any thoughts on that.
Yes, I think that's, if you look at any individual storm, it's something we're looking at the moment, and of course we do event attribution here, then you often find that, like event attribution will often find a consistent contribution to intensity from rising greenhouse gases and anthropogenic forcings. So there's always an element of it now, but extremes have always happened. But as David said, there is no excuse for not planning for ones that have happened already, and the projections show that records get broken in the future. So we do have to build in some resilience, on top of the ones that we've seen already. We need to kind of uplift those a little bit as well. But I think there's still a lot of stuff we're trying to understand about the extremes. For example, I have someone in my team who's trying to understand whether climate change is actually changing the nature of the variability of the circulation patterns that potentially set up some of the extremes, especially the German one, because that was the London German one that followed the heat dome in Canada. So it was all part of the operation meteorologist thing. It's all part of the same kind of system, just shifting through over a period of time. So there's a lot of interesting science still to be done on that. Yep.
Okay, just one final one. This is from Sean Wilkinson and Dave. Sorry, this is directly to you. How confident are you that the model replicates the large-scale atmospheric features? That the model replicates large-scale atmospheric features, especially considering how the jet stream has been changing. So, how well is it captured? How well are the models capturing the jet stream and other synoptic scale? And you mentioned about the connectivity, the teleconnections between heat domes in one place, etc.
Yeah. So we tackle that on different respects. So on average, actually, the current set of Met Office global runs actually do quite a very good job of actually capturing the jet positions, or the three prominent jet positions that you get that affect the weather in the UK. And actually, in these runs in the paper, I kind of analyse the connection between the jets and the weather types, and it does tally. It does hold up very well. So the model runs are doing much better than they used to, but I still think there's open questions about some of the quality of how the models represent some of the really important maybe changes in the jets that create the extremes, specifically things like the heat dome. So models, Ben Sanderson, who's a kind of international scientist, he did an analysis. None of the CMIP6 models actually could create a heat dome over Canada. But there's also someone else who's, if you give the initial conditions, like a forecast 10 days on, the models are actually capable of reproducing the heat dome. They just have to be told about it. They just won't sample at the moment. So there is still work to be done. And another paper I've written recently kind of suggests that there's still room for improvement for the models to kind of capture the effects and links between the tropics and the extratropics to affect the jets. So there's definitely work to be done, but they're certainly better than they were, the models.
Okay, Dave, thank you very much. We're drawing to a close now. There's just one general question here from Sam Gardner about the next whole-scale UKCP update. Now, I think that's watch this space. To do the UKCP experiments is complex, time-consuming, and costly. So there are probably plans in place, but we'll see about that in the future. And finally, no one answered my question. I'm very disappointed about it. You've got to get this ready for Christmas quizzes and all that. What has to be lower than minus 34.39 Celsius for the remainder of the year? That's the Central England temperature. Below that to beat the coldest year ever recorded in the Central England temperature. Now, there you go. Fun fact. The converse to that, I can be corrected on this. It's got to be about 2.8 degrees above the average to beat the record CET. So that's not beyond the realms of improbability. But the coldest year on record is going to happen. We need more than woolly jumpers. Right then. Okay. Sitlali, do you just want to mention? There's a survey. Do you want to just mention about that, Sitlali?
Yeah, thank you very much. We're trying to gather some feedback about the UKCP webinars. Again, your contribution is very useful. We'd like to know. Last time we had a few participants but we understand it was the middle of vacation. So basically, we are getting the feedback that the webinars are useful, and we have some information on what would you like to see more and less. If you'd like to answer the webinar, the question, please go ahead. It's less than 3 minutes. It should be very quick. But yeah, if you're finding this useful, please consider writing to us and presenting with us. Your information is important for this contribution at any point. Thank you very much for joining in any case, and thank you very much again to David Weiner and David Sexton for such an interesting presentation. Thank you very much.
Well, yeah, thank you very much, Dave. And remember, this is your community, your network. So let's get all involved, and yeah, let's make this more positive. Let's make it. I'd like to see the whole thing become a lot more inclusive as well, with different people and different agencies and organisations getting involved. So please share the word and share the love. Thanks a lot. And we don't speak to you before. Have a great season, and Christmas and holiday period and all that. Fantastic. Thank you.